So let's start our lecture today. We continue with the theory of self-adjoint extensions of operator, of symmetric operator. But to construct this extension, we need additional notion, isometric and unitary operators. So definition, let H is Hilbert space. Operator V from H to H is isometry or isometry operator, isometric operator. If for any x from the domain of V, and it can be defined not on whole space, on some part, the norm of Vx coincide with x. So it is preserved norm. So it is easy to show that for any complex number z which do not lie on the unit circle, it is a field of regularity. So statement, if z is not on the unit circle, then z belongs to the, I remind it's field of regularity. It's almost resolvent set. We have an inverse operator, but it is not defined on all, only on the image of operator, on the range of operator. So how we show proof? I try to do this. And these coincide by definition of isometry with the norm of x. But this is not 1. This number is not 1 because we make this assumption. So we immediately obtain that this. So it is not, it is positive number. And if we have such inequality, it is a we know that it exists in the inverse operator. But it's defined only on the range of operator. Okay. So this is field of regularity. So you can define again two numbers, defect numbers or deficiency index. Yes. For a symmetric operator, we define two numbers in the up half plane and in the low half plane. Yes. For I remind that A is symmetric. It is lies. It is equivalent definition of symmetric operator. We have n plus of A. It is dimension of the range A minus I orthogonal. And n minus A, it is dimension of the range A plus EI orthogonal. So plus because we take I from the half plane, for the positive imaginary paths. We showed last time that this is constant for all lambda from the all half plane. And for simplicity, we take imaginary unit. So we have two defect numbers, or deficiency index. And similar, we can define two defect numbers for isometry operator. What are they? If the field of regularity is all complex numbers not lying on the unit circle. So you have interior defect number and exterior defect number. So we can define an exterior of V. It is yes, and exterior defect numbers the same. For and to know that in connective component they are constant. Yes, we have two again for isometry operator, for symmetry operator we have two components of connectivity, upper and lower half planes. For isometric operators, we similar have again two components of connectivity: the interior of the unit circle and the exterior of the unit circle. And so it's easy to see that we know that if you have a strongly subordinated perturbation, the defect numbers are coincide. Yeah? We proved it last time. If we have one operator and we perturb this operator by smaller operator, which is strongly subordinated, then deficiency index are the same for operator A and operator A plus B. So, for example, here the norm of this operator is 1. It is isometry. And here Z is less than 1. So this operator is subordinated to this operator, of course. Yes? Because the norm of isometry is 1. For the norm of isometric operator is 1. And if we take Z smaller than 1 inside, then it is a perturbation, a small perturbation. It is subordinated because the norm of this operator is smaller than this operator. So the defect number of this operator is the same of this operator. So you can see that this is orthogonal complement. Yes, you can take what Z. You can take Z equal to 0. Because so it is for two arguments, for example, again, I can repeat, because this operator Zi is strongly subordinated to V, it is first argument. Another argument, in component of connectivity, the defect numbers are the same. 0 is inside this unit circle. So for any Z smaller than 1, the defect number coincides with the defect number for operator V when we take Z equals to 0. How we can change this situation? Here this operator is larger. The norm of this operator is Z, which is larger than 1. And then this operator V have norm equal to 1. So they change their roles. This is strong operator, this is small operator. It's strongly subordinated to this. For bounded operators, the strongly subordination is just that the norm less than norm of origin operator of perturb operator. Yeah, clear? So here you can take away this, because it is subordinated. And Z, it is scalar. So it is just a domain of operator I on V. So it is dimension of dV. The domain of V. The domain of V. The orthogonal. The orthogonal for dV. So it is. And when operator V is unitary operator. Unitary operator is isometry and bijective. The problem that we have here, we have domain. So it is isometry is not defined on whole space. But if isometry is bijective between H and H, then it is unitary operator. Okay? So let V is isometry, isometric operator, and then V is unitary if V is bijection. So it is bijection which preserves norms and or preserves scalar product. And now what you can say about here we have defect in the range, here we have defect in the domain of operator. So you can conclude when in the terms of defect numbers when the isometry is a unitary operator. Again, this number describe us the defect in surreactivity, the orthogonal to the range. And this defect number describe us the defect in the injectivity. So, sorry, it is full. Isometry is always injectivity. But it is all these numbers describe as the defect in the bijectivity, bijection. So unitary operator, isometry operator is unitary if and only if these defect numbers are zero. And we know for symmetric operator is self-adjoint if and only if these numbers are zero. We showed it last time. So now we try to use this fact that, and try to construct the theory of extension of operator, symmetric operator, with the help of isometry operator. So Cayley transform. Let's A symmetric operator, define operator V. This operator is named Cayley Transform. We know that the inverse operator for this operator exists because we show that for lambda which equals alpha plus E beta and beta not zero, we show that this inequality valid, yeah, by for symmetric operator. So there exists inverse operator. So there exists inverse operator. But where it exists? What you can say about the domain of operator V? What vectors you can put here? Inverse operator exists only from the range of operator. So here you can put what vectors? Only from the range. And the action of operator V, what you obtain? Put it here, this place. So this operator reduced with this operator, because it is inverse for this operator from the range. So it is more precise definition of this operator in details. This is only formula for this operator, but we must describe the domain of operator and the action of operator. So by this formula, we take the domain of operator as the range of this operator, and the result of acting of operator is this vector. Okay? So, and now you can prove that this indeed isometry. So theorem. Why? Because do you remember the result of this, how we prove it? The main idea of proving this. The main idea of proving this, we write the quadratic form of this operator. We write this, not quadratic form, we write the square of the norm. Then square of the norm is the inner product of the vectors on itself. Yes? And then we take away all brackets, and this equals a minus alpha I x plus beta square x square. But here we have alpha equals to 0 for simplicity. Yes, so this ax square and plus x square. Beta equals to 1. And now calculate this. The difference only in the sign of imaginary unit. Plus I here minus I. And it doesn't matter on this. So you see that it is equal to the same number. Okay, so it is a symmetry. So it is a symmetric operator, because the norms are the same. So we have correspondence between symmetric operator and isometric operators. The question, is it one-to-one correspondence or not? Can we obtain any isometry? The answer is no. Answer is no. So let's consider some properties of operator V which we obtain by Cayley transform. So let's write here, because we use this formula very often today. So domain of operator V equals to the range of this operator. So y equals from here equals, and V on y acts as a minus I ix. I repeat this formula because we need it today very often. Property of operator V. It is not property of arbitrary isometric operator. It is property of isometric operator which we obtain from the Cayley transform. First property, I state that is not in point spectrum. So we can define the inverse operator V minus I, minus indent, because operator is injective in this situation. It may be unbounded, but the operator exists. And second, I state that the range of this operator is dense. Is dense in H. The closure of the range of this operator gives us whole space. So first this, if exists Y such that Vi equals to I, definition of the point spectrum, yes? Then take these formulas. Take these formulas and write it. So we immediately obtain what? When it is possible, x is 0, then y is 0. So it is not an eigenvector. Because eigenvector must be not 0. Then, if range, okay. Second, this. Let exist Z which orthogonal to so it means that scalar product is 0 for any y from the domain of V. Let's again take these formulas. Hello. Take again these formulas. So what we obtain? But we consider symmetric operator with what property? I don't write it today, I forget about this. But on the previous lectures, we emphasized it. For what symmetric operator we consider? With what important property? We consider symmetric operator with the dense domain. With the dense domain. Without this assumption, it is impossible to to determine the adjoint operator, if you remember. We can define correctly adjoint operator only in this situation. So it is always valid for us. For our theory, it is always valid. So we obtain this. This does matter on the 0. Yes, it is 2 imaginary units, and but from the second place. Yes, and so plus without minus, because I take away these numbers from the second place. So this vector is orthogonal to any vector from the domain. And now this assumption works. The domain is the dense set. So by continuity of inner product, then we obtain that Z orthogonal to all space. Yes? Because this is dense. So Z is 0. So it means that the range of this operator is dense.
Can you repeat this again? Can you repeat this again? What you just said?
We prove that the range of this operator is dense. I suppose that there exists some vector orthogonal. If it is not dense, must be a vector, then the closure is some subspace. There must be exist a vector which is orthogonal to this subspace. So we assume the existence of such vector, but we show that this vector is 0. So it means that this set is dense. Yeah? Because if it is not dense, again, then the closure is some subspace, non-trivial subspace. Then must be exist vector orthogonal to this subspace, non-zero vector orthogonal to this subspace. We prove it the lemma of orthogonal complement. But in a real situation, we need all these demands. Sufficient only this. So let's show that if we have this property, then the 1 is not from the point spectrum. You can see that they are very similar. Here we have this identity, yes, when we prove that 1 is not point spectrum. And here we have the same situation. So they are very similar to each other. So let's show from the 2 we obtain 1. So statement. Let V is isometry and the range of V minus I is dense. Then the 1 is not from the point spectrum. Let exist X such that Vx equal to X. So it is the same thing, yes? So for any from the domain, we obtain that equals to 0. Because this is 0. Vxz but our operator is isometry, it preserves in the product. It preserves scalar product. So this scalar product equals to this scalar product. And this is up to the sign is the range of operator I'm identity minus v, yes? When we take arbitrary z from the domain. But we know that this range is dense. And we have a vector orthogonal to the dense set. What you can say about vector dx? Is 0. But we have this identity. Contradiction. So then have x is 0, it is not eigenvector. Because eigenvector is not 0. And now we can obtain that we have one-to-one correspondence between symmetric operators with this property and isometric operator with this property. Yeah? So theorem. And this. Moreover, this arrow we obtain, yes? We take the symmetric operator with Cayley transform, by Cayley transform. And by Cayley transform, we obtain the isometric operator with this property. We just show it. So what we need to go to another direction. So we need to show this. So let V is from this set. Isometric operator with dense range for operator V minus I. So we have these formulas. I write it here. So let's try to reconstruct operator A. Let's reconstruct the operator A. We have 1 and 2. If I subtract from the second line this line, 2 minus 1. What happens? Left V minus I, yes, and here we obtain and this is just a constant. I can divide it, but this is a range of operator. It is linear space. So this constant doesn't matter. So we obtain x mass line in domain of operator A. By this equality, you can conclude that the domain of operator A coincides with what subspace? With the range of operator V minus identity. So x must lie here. So we obtain that the domain of operator is the range of this operator. And this is dense, so we obtain that this is dense too. So we obtain the first object for operator is the range of operator. And how we can obtain the action of operator? When we obtain the domain, we consider subtraction. if we want to obtain the action of operator A, what we do with this? Plus. And so AX is 1/2 V plus I Y, and Y is and we know that this operator exists. This operator exists because 1, we show that 1 is not in a point spectrum. So if we put it here, so we obtain that AX equal to what? Yes? This 2 and this 1/2 reduced. We obtain minus imaginary unit, operator V plus 1, and except Y, I substitute this formula. So we obtain this. So we obtain the operator, and what we need to show for this operator? We know that the domain of this operator is dense, because it coincides with the range, which is dense. But what we need to show for operator A, additional? Yes. This property. So let's check that this is symmetric, and for symmetricity of operator, what's sufficient to do? Is it clear that the operator is symmetric if and only if the quadratic form is real values? We know by definition of symmetric operator that for any xy from the domain, we have this property, yes? Let's consider the quadratic form of this operator. For any x from the domain. For one side, you can put it here by the definition of properties of inner product. If we change the arguments by places, we'll obtain the conjugate number. So it is a real value. And inverse is true. It is more sophisticated, but it is like exercise. If quadratic form real, then you can show that this operator is symmetric. So you can put it, change the place of this operator in the inner product. It is possible to do if we rewrite the quadratic, if we write the semi-square linear form with the quadratic form. It is a long formula, but it is like look, I write quadratic forms. Yes, he had quadratic forms. If we and 1/4 very long formula here I might be forget, but like plus or minus this ax plus iy x plus iy minus a x minus iy, x minus iy. Like something like this. So we can write the semi-square linear form as linear combination of quadratic forms. I don't remember the sign here. But we know that they are real. If we know the quadratic real, that it is an imaginary part. It's a real part of some number and imaginary. Then you change and write this. Change all elements here, and you can check that they coincide. This idea of this, but it's a long writings. But the idea that you can write semi-square linear form of operator with the help of quadratic form. Of course, we work in a complex space, because in real space we need to show that the quadratic form is real. Because for any operator it is real, so there are no sense in this statement. So statement valid only for complex space. If operator have real quadratic form, then it is symmetric, if and only if. So this is up to exercise, yes? Main idea to show that operator is symmetric is it is sufficient for us to show that quadratic form is real valued. Okay. So it's sufficient. Okay, let's try to do it. What is AX? AX is here, yes? What is the X? X is here. Okay? I just take our formulas and write all these elements. So here we have 1 over with plus for I, yes? I take it away from the second argument. And what we have here? We have this. And this is brackets for scalar product. Oh, okay. Let's take away brackets. Vy minus plus y vy and minus y. So what you can say about first and the fourth terms? Okay, cancelled. Because operator is isometry. What you can say about second and the third? You can change the elements here, and you obtain that it is vyy conjugated minus no, it is conjugate number. V is not symmetric operator. V is isometry operator. But this is some complex number. This is, for example, alpha plus E beta. This. So with minus. And here is a conjugate number, so it is alpha minus I beta. Yeah? So alpha cancelled. Beta with imaginary unit twice. So it is pure imaginary number. Okay? It is pure imaginary number. But here we have additional imaginary unit. They reduced. So you obtain that all this number is real. So this number is real. So we obtain that the operator is symmetric. So we can describe the domain of a joint operator to the symmetric operator. So let A is with the dense domain, so it has a joint operator. Then I just look in what order I write not to mismatch this. First minus k. It doesn't matter, but it is for convenience. So the domain of any joint operator for symmetric operators can be represented in this manner. Yes, we just prove it. But one inclusion is simple. This is obvious. Because all terms are from the domain of operator A star. By definition, we know that A lies in, from the definition, the equivalent definition of symmetric operator is the joint operator is extension of operator A. So the domain of operator A lies inside the domain of operator A star. So this is from the domain of operator A star, and this is obvious is from the domain of operator A star, and this is from the domain of operator A star. So this inclusion is obvious. Yes. So what we need to show. So it is obvious. The inside inclusion. The inside inclusion. And moreover, I don't say about it, but this sum is direct. It is direct sum. In addition, we'll show it. So we have, on the previous lecture, we showed the representation of whole space as for, we can, yes? Let's have a look. Yeah. But again, it's better to take here minus and here plus. In general situation, we must take closure of operator, of the range. But your operator is symmetric, and this is, number is not real. It is pure for any complex number with a non-zero imaginary part. I write it. We have such estimation. Yeah? And from this estimation, we can conclude for the closed operator, we have closed operator, then range of operator is closed. But I don't write here, let's symmetric operator, dense, and A is closed. Because we can show it on for the closed operators. Just now we work with unbounded operators. But for closed operators, it is true. This, that if we have such estimation, then the range of operator is closed. Need I repeat why it is or not? We prove it for bounded operators, but for unbounded operator, it is valid too if we consider closed operators. Because for closed operators, you can take the limit procedure on the domain. By definition of the graph of operator is closed set. Now, for example, if you consider let y is a limit point of range of operator A minus lambda I. Lambda here is alpha plus E beta. If is limit point, what you can construct? Then they exist yn from the range, yes? And yn tends to the y. From this inequality, you immediately obtain that xn minus xm yes, from this. So it is a converging sequence, so it is fundamental. What you can say about the fundamentality of xn? It is fundamental. So it converges to some element x. And by the definition of the closed operator, what you can say about element x? If it belongs to H, if A is closed, then X belongs to the domain of operator and AX equals to Y. It is just a definition of the closed operator. So here it is important thing. That's why we need to write the closure. Because this range is closed. This range is closed. And so let's take the y from the domain of operator A. And let's write then this vector. It belongs to H in this representation. You can write the result of vector of operator A star minus I identity to the Y. It is some vector from the Gilbert space H. You can write this vector in this representation. So there exists some element x from the domain of operator A. And again, the kernel of operator, of any linear operator, is linear subspace. Yes? So you can multiplicate any element from this subspace on any number. And it belong to this subspace. As number, I take -2i. You can write here any number. It is just, this is from the kernel, this is from the kernel too, yes? Because it is linear subspace. Why it is convenient to write this? Because by definition, AU equals minus IU, yes, because it's from kernel. And A star minus equals to what? From this. Minus 2IU. That's why I take this number. Because I can write it as action of this operator. And additional, we know that A star on the domain of operator coincide with which operator? A. Because for symmetric operator, the adjoint operator is the extension. And so you can write this equation. So again, this is equality by this representation. But some tricks with the constants and tricks with the domain of operator A, in what way you can rewrite this equation? Is it clear? Here you can change A on A star because X from the domain. And here we calculate that minus 2IU equals to this. So you can change on this. And then take all take to the left side. Is it clear? So what you obtain? This, denote this vector as vector V, where it lies by this equation. In the kernel of this. Yeah? So we obtain that. Remember, we take arbitrary vector from the domain of operator A star. And we obtain that it's equal X plus U plus V. U is from the kernel of this, and V is from the kernel from this. Another order. We'll change the order of the summation. X plus V plus U. Okay? Clear?
You said this was direct sum.
Yeah, I don't show it. Yeah, I don't show it yet, but we show you. Yes, but we obtain this representation.
Yeah.
We obtain this representation. Why it is? If we want to show that the sum is direct, it is sufficient to show that zero have a unique representation. Okay? Because if we have two different representations of y, x prime plus u prime plus v prime for the same y, yes? If sum is not direct, then it is possible. But then you can write, subtract from one line another line. So here you obtain 0, yes? And here you obtain the 0 from x minus x prime is from the domain of A. U minus u prime, it is from the kernel of A star plus I. And v minus v prime is from the kernel of A star minus I. So it is sufficient to show that if sum is direct, it is sufficient to show that 0 have unique representation as sum of vectors from these subspaces. Okay? Just standard arguments for direct sums. You have another. So direct sum have unique representation, any vector. So if we have different, so the subtraction, we obtain that the 0 have some, maybe not 0 representation. Sum is direct. Let's show it. Let sum where x from the domain of operator A, u from the kernel of operator A star plus identity, and v from the kernel of operator A star minus I identity. So take some, but I don't guess what operator take. This operator or this operator, and act on this sum of some of these operators. Let's act by this operator. Oh, not this. This. By this operator. So what we v is cancelled, yes, because it is in the kernel. X is from the domain, so on the domain of A we can write the A star as A. So we obtain that it is A star A minus I identity X plus equals to 0. But u is from the kernel of this operator. So for u, what we have? For u, we have A star u equals minus I u. So here minus I. So it is means we have some representation in this sum. The range of operator A plus kernel u from the kernel of a joint operator. But we know that this sum is not only direct, it is orthogonal. It is orthogonal, in particular it is direct. So when it is possible? When all are 0. So u is 0. So u is 0, and A minus II x equals to 0. But it means that I is the point spectrum of symmetric operator. But half plane, upper half plane, and lower half plane are the field of regularity. Operator is injective. For the field of regularity, we again have the, if lambda belongs to the field of regularity, then we have this property. Yes? For some positive constant. And if we have such property, then we have inverse bounded operator from the range of operator. And if we have inverse operator, operator must be injective. If it is injective, point spectrum is empty. So non-real numbers can't lie in the point spectrum of symmetric operator. So it means that x must be 0. Okay, clear? So we ax equals ix is impossible. For x which is not 0. For x which is not 0. Okay? Clear? So we prove it. And the main idea, how to construct, how to describe the self-extension. Some naive approach. I start with this. So here I write the axis domains of extensions of symmetric operator A. We have here domain of A, and here we have domain of A star. It is larger. The main idea, find some reduction of, reduce in some sense the domain of operator A star, then the domain of A can be larger. To find some restrictions on the domain of this operator. If you take some restrictions of the domain of a adjoint operator, it lies here, yes? Then the domain of operator S became larger. So we find some extension of operator A. It can be here, but then it's not self-adjoint, yes? If we want to find self-adjoint extension of operator A, you must find such a restriction of this domain, that the domain of restricted adjoint operator coincide with the domain extended of operator A. Is it a clear idea? I remind you example. I take away this part, theorem. I remind the example of operator A, F, E, F star in L2, 0, 1 with the domain Sobolev space with the Dirichlet boundary condition. Function at 0 and function at 1 equals to 1, to 0. We show that this operator is symmetric, but it is not self-adjoint because the domain of the adjoint operator is the Sobolev space without any boundary condition. Without any boundary condition. So here you can find these ideas. You try to find some restriction on this domain. Then automatically this domain extended. And if they coincide, you obtain a self-adjoint extension. And the idea to find the restriction is here we have kernel of this, and here kernel this. Some connections between these kernels. The idea to construct self-adjoint extension is something interlacing rule with these kernels. Okay?
So we need to prove the dimensions of these two.
And we know the one-to-one correspondence between symmetric operators and isometry operators. It's short idea. You take symmetric operator. By Cayley transform, you construct isometry operator. And we know the defect indices of these operators. And I don't show, but I just discuss it. For symmetric operator, we have two defect numbers. And for the symmetric operators, we have two defect numbers. They are coincide. One number for symmetric operator coincide with one number for isometry operator. Another number coincide with another number. And if I think we can take away this theorem. Please. Please look what you write on the first part of my lecture. We have interior number and exterior number for isometry operators. Interior number coincide with the range of dimension of orthogonal of this. And this coincide with this orthogonal. Please look what we write. orthogonal. And one number coincide. You can write here. Look here. We have this. The domain of V is the range of this operator. Look that here. This is n minus. Yes? So we have that this is n minus. Yes? And n plus is the range of this. It is the range of operator V. Yes? The range of A minus I identity is the range of operator V. So it is n plus. And so it is sufficient to construct some isometry between these two subspaces. So you see that our operator V is unitary if and only if these two numbers are zero. We have no defects in the range and in the domain. So idea to construct, from the symmetric operator, we construct by Cayley transform some isometry operator. If it is unitary, our operator is, if it is unitary, then these defect numbers are zero. Then these defect numbers are zero. So our operator A is not symmetric. It is symmetric, but it is self-adjoint. But if these numbers are not zero, what you can do? You can construct some operator from this subspace to this subspace. So we have operator V, and you can construct new operator V plus V0. V0 is some isometric operator between this to this. You can, so you, but if it is isometry, then the dimensions of these spaces must be the same. Yes, they must be coincide. So if you construct, will be some extension. It is new operator, isometric operator. Then you can construct. We find the formulas. Yes, of how we can reconstruct the symmetric operator with the help of isometry. We have one-to-one correspondence with the class of symmetric operator with dense domain, with the isometry operator with the dense range of V minus identity. We have one-to-one correspondence. So take symmetric operator, construct isometry operator. If it has defect subspaces, construct the direct sum, our from Cayley transform and the new additional operator from these spaces. And then come back to the symmetric operator. If these dimensions are the same, you can construct the full isometry, the unitary operator. Then this operator will be unitary operator. Okay? And then if it is unitary, then these numbers are zero. Then you reconstruct operator A, the defect index are coincide, so these numbers are zero, then so you obtain the self-adjoint extension. It is not technique, it is idea, so we just write some formulas for this. But this is only as idea without technique. But we have connections between these spaces and these spaces. Yes? It is more correctly, it's more convenient to write the isometry not from these spaces, but we have definition, we have representation that dA star equals dA plus ker A star minus AA plus ker A star plus AA. So let D0 some subspace in ker and R0 are subspace from this space. So take some subspaces with only one assumption. they have the same dimension. And then we construct some isometry between two subspaces. Moreover, not isometry, unitary operator. It have the same dimensions, so you can construct unitary, some unitary operator. And then is the domain of some extension, some symmetry extension. Unfortunately, I take away these formulas, but we can just, we have some rests here. When we write difference, 2 minus 1, we cancelled a, so we obtain x is just a domain of operator a, yes? So v minus I is the domain. Why we have here v0 minus I? It is just extension of the domain. It's the domain of symmetric operator. Yeah? So it is really it was our operator, origin operator, and we have extended. How? We have some defect spaces, and we construct, we take some subspaces inside these kernels and construct arbitrary unitary operator from these spaces. It is possible if the dimension of these subspaces coincide. And then by these formulas, we obtain that this is a domain of some symmetric extension. And how operator acts on this extension? Can you write how A tilde, the extended operator, acts on these vectors? Here we have x, and we have some vector v from D0. On this x, what happens if it is extended operator? Yeah. And here what we have? Here we have minus D0 identity operator, so minus V. And here V0 acts on the D0. We obtain what operator? We obtain operator from this. Yeah. V was in what space? In D0, which lies in the kernel of operator A star minus II, yes? So A star V equals IV. So here I take IV. And V0V belongs to RA0 and belongs to the kernel. It's part of the kernel of this operator. So A star V0V equals to what? Minus I. So this is the description of the action of the operator. This is some domain, and this is the result of the action of operator. We interlaced these spaces by unitary operator. Not spaces, but subspaces. But if defect index of operator A coincide, it means that the dimension of these spaces are the same. So you can construct the full unitary, not from the subspaces, but the full unitary just from this space to this space. And all self-adjoint extensions depends on what? How many unitary operators you can construct from the D0 to R0. For example, what you know, little blackboard. And adjoint operator this operator. So what you know about these kernels? We calculated on previous lecture. We calculated the defect numbers. Yes. For here we have sign plus, and here we have sign minus. If you want to construct operator V0, what you must to do? If you want to construct isometry, you must be sure that it preserves norms. So first you must normalize these functions. It is a lot of calculation. So I divided on, you must find this. So the norm of this operator is vector 1. The norm of this vector is 1. We have one-dimensional situation for this operator. The defect numbers are equals to 1, 1. Defect numbers equals to 1, 1. So space D0 is the linear span of this vector. Space R0 is the linear span of this vector. And they normalized. How you can construct V0? One-dimensional situation. What is unitary operator in one-dimensional situation? Multiplication on number with absolute value equals to 1.
Can we just map it to that E minus 6 divided by 1?
If it is not unit, how you don't know on what number you must multiplicate. If the norm is 1, then unitary operator is multiplication on number with absolute value equals to 1. But so the 0 equals to some gamma on this. And the choosing of this gamma is a description of all unitary extensions. But it is a difficult way. Nobody doing this in such way because it is a lot of calculations. A lot of calculations. What calculations? Norm of this, norm of this. Then we have domain of this, and then you can recalculate. So you can find, so it is something function. So so here we have gamma minus 1 v0 gamma a minus x divided na norm minus x minus we have some interlacing between these situations. Then you can calculate the values at 0, and then you can calculate the values at 1 of this new function, of this new function. And then you can guess that you can obtain the self-adjoint extension in another way. What? You know that the fact numbers 1, 1. So you have one parametric family of self-adjoint extension. What are they? You must, this is very strict, strong restriction of the domain. A function at 0, 0, a function at 1, 0. So we have no restrictions here. No boundary conditions. So idea, find the symmetric boundary conditions. So such boundary conditions that when you can integrate by parts, the non-integral term go to 0 by symmetric assumption for function. You can obtain this assumption from this, but it is a long way. So you can try to guess that. I write it on the last lecture. Theta is not gamma, it is another number, but absolute value of this number theta equals to 1. So you obtain self-adjoint extension, all self-adjoint extension for this operator. It depends on one parametric family theta.
So why did you wrote here in expressions plus minus I?
Because I take D0 from this and R0 from this, the kernels. So this is just a kernel. This is kernel of this operator, A star minus II. Because you can rewrite it A star minus II F. Also, here not prime. Prime is just here. This is, oh no, sorry, it is definition of operators. It is definition of operators. And this is equation for eigenvalues and eigenvectors. So this is equals to 0. Take this to the left side. So first upper sign is for this kernel, lower sign is for this kernel. So this function is with sign plus is from D0, and function with minus is from R0. And you construct as isometry between these two subspaces. Yeah, this is exponents. But if you want to try to find just isometry, you must check that the norm of these functions are the same. For example, equals to 1. Then unitary operator is just multiplication on number with absolute value equals to 1. Just I write this. I can write this, just these formulas, because once upon a time I calculated. So in more details, what we have for this operator, for our operator. It is linear span of this. It is normalized. Do you see? This is just divided on the norm. Then the norm of this vector is 1. R0 looks like this. You can check just when you calculate the norms, you obtain this. You obtain this. And V0 and gamma must be 1. It is just operator V0. In you have this one-dimensional space and this one-dimensional space. All unitary operators is multiplication on number with absolute value equals to 1. You can take arbitrary number. You have a lot of extensions. One-dimensional family of extensions. Take one gamma, you obtain one self-adjoint extension. If you take another gamma, you obtain another self-extension. And in terms of boundary conditions, it is just taking, we have this 0 and this 0 for our operator A, for symmetric operator. But for self-adjoint extension, we have only this. We have interlacing the values at 0 and 1. For 0, 0 here, it is true 2, yes? Because we have that the domain of a self-adjoint extension is dA plus something else, some restriction. Of course, these restrictions such that for domain of operator A, it must be valid. For example, from function for this space, this is valid too. But you have an additional value. So you can check that you can write this function v0 minus I, this, and check what you, so you write gamma minus what? This. This is function f. It is additional function. It is restricted function from the sum of these two subspaces. We interlaced it with some unitary operator. So you can calculate f at 0, what you have? What is the value of this function at 0? Gamma square root 2e is e square minus minus square root 2. Yes, this. What you have f1 gamma e1 minus this cancelled, you see. And try to find some laws which connect these two values. What is theta? You can calculate it, find theta through the gamma. Through the gamma. It's just an example how you can construct. It's only one-dimensional situation. You can imagine what happens if you have two-dimensional spaces, defect spaces, three-dimensional defect spaces. But if defect numbers are different, you can construct self-adjoint extension. You can construct only symmetric extension up to the situation when one defect number is equal to 0 and another defect number is not 0, because you construct isometry. By isometry, you can take away the subspaces with the same dimension.